All right, hello everyone. Today we'll be talking about one of the two graph traversal methods. The one we're going to be focusing on today is BFS, and then later I'll make another video on BFS, so feel free to check that out when I finish uploading that. All right, so right here I have an image that shows how these graph traversals that it shows the order in which they travel the nodes in two exact same binary trees. So this one is DFS. We won't be focusing on that today. So I'll just go ahead and cross it out. But we're going to be focusing on BFS today, more commonly known as breadth first search. And as you can see in the picture, it's basically a level traversal of the tree where it goes from the first level to the second one, to the third one, to the fourth one. So that's what is commonly known as BFS, and that's what we'll be taking a look at today. And then let's head over to the more in-depth slide over here. All right, so BFFs involves searching the nearest levels from the start node first. Then it takes the child nodes of that node that it traversed and stores it into a queue. And this right here is very important. It's basically the core data structure of a BFS traversal algorithm. And then it repeats the process for the current items in the queue until the queue is empty. And one of the main reasons you use a queue is because, well, it depends. It could be first in, first out, which is the one you want in this case, because you want to maintain the order of that level. So if we go back to this picture over here, right here, I'm just going to give you a simple walkthrough of what a BFS traversal will look like here. So first, what would happen is it'll take this node. Well, this nodes are going to be already in your queue because this is your root. So you're going to have this node in your queue. And what happens is it will add these two nodes in. Well, I guess first what happens is you want to pop this and you want to get its value and its data. So first you'll pop this from the queue. So this gets popped from the queue. And then you got its value, and then you will print this value. Then you get its data. So as you can see here, its child nodes are B and C. So what happens next is you add B and you add C into that queue. And this is where a queue comes in. Because the default queue is first in, first out, in the next level, it'll pop the B first. So then B gets popped, and it stores D and E after the C. So now it looks like C, D, and E. And then it pops the C, so C is now out, and it stores F and G. So right here is F and G. All right, so now it gets to D. Pops D, puts in H and I. I won't write it, but you know what I mean. Well, actually, I made a mistake here. I is the child node of E. So what happens is it pops D and gets H, and that's all, because H is the only child node of D. And then what happens is it moves on to E. So D is popped. Now E is popped. And notice E has two child nodes. One is I and one is J. So it adds I and J to the end of the queue. And then it pops F. Adds K. And then to the end of the queue. So now the queue only has H, I, J, and K. Now it gets to this G here. Because the G doesn't have any child nodes, nothing will be added into the queue, and it'll just go on to the next level. So now with H, I, J, and K, what happens is it pops the H first. It has no child nodes, so it does nothing. Same with all four of these. And then the traversal is finished. This might feel a little intimidating, but in reality, it really isn't. So we're actually going to do an example now. So right here, I have this image that I just searched it up on Google. I think it was from Computing and Technology. So I have this image here. This is an n-ary tree, which means the tree is not restricted to 2 child nodes each. So I chose this image because this was easy to replicate in the code for the data. So I chose this tree, and it's a good example of what you might what an it's a good example of an implementation of a BFS algorithm. So they named their nodes 1, 3, 2, 4, 5, 6. For simplicity reasons, we're just gonna subtract 1 on each value. So the actual tree looks like 0, 2, 1, 3, 4, and 5. And that's just for, I mean, it doesn't really cause much difference, but it's just for my array indices. So keep in mind that this is the tree, the n-ary tree that we're gonna do a level traversal of, and let's head over to Intellij. Okay, so here I have the init function. When you do most graph questions, what you want to do is you want to either put it into an adjacency matrix or an adjacency list. I guess I actually named this wrong because it's an adjacency list here. So the difference between an adjacency matrix and an adjacency list is that, as you may know with matrices, the width is fixed. So if the width of your row I is 5, then all of your rows width are 5. So what might happen is when you insert your child nodes into your parent row, which is, so say you have a tree like I, then I, and then K and L. So pretend that K and L are child nodes of I. What you would do is at row I, you would put K and L into that row, and that the cells filled with K and L represents the child of I. Now the difference here with an adjacency matrix and an adjacency list is that an adjacency list, because you're using a list data structure, the size is dynamic, which means you won't actually have any unnecessary data. So if there was more nodes down, for the child node of K and L, then for an adjacency matrix, what would happen is you might have empty cells that are just like 0 sitting around, and K and L, and there's only 2 child nodes. So really the benefit of an adjacency list is it'll be faster for traversal, and it saves a lot of memory. All right, so now I'm just gonna print this list out so you can see this adjacency list thing. I should probably call the init function. There we go. All right, so remember here we renamed our nodes. So this is 0, 2, 1, 3, 4, and 5. Okay, and then let's head over here. So at index 0, these 3 values represent the child nodes of 0. And as you can see here, it's 2, 1, and 3. All right, so this is 1. This list right here represents the child nodes of 1, which as you can see is empty, and it's empty over here as well. This one represents the child nodes of 2, and the child nodes are 4 and 5, and Over here, it's 4 and 5 as well. And the rest are empty because they don't really have any nodes. And that's the data structure. Well, that's how we're going to store data for our graph. Okay, now we're going to do our BFS. So, as I stated earlier, we're going to use a queue. That queue will hold the value of your node. Now, the only reason we can hold the value of our node right now is because we don't have any duplicate value nodes in our tree. When you have duplicate value nodes in your tree, you won't be able to store just the value of your nodes because that will actually mess up your program. You'll probably either have to go remark your tree so that every value is distinct, or in the parameter right here, you would pass in the individual data of your node. But right now, because all of our nodes are distinct, we can just enter the value and then take the role of this adjacency list and traverse that instead. So I'll call it Q for Q, and maybe this is weird, but a queue is actually a linked list. That's just the way it is. All right. And then one mistake that a lot of people makes is they forget to add the root node into the queue. And what happens if you don't add the root node is that your queue is always empty. So you don't get a traversal from that. So we're going to remember to add a root node, which is 0. And then we're going to have a while loop. So while the queue is not empty, right? If the queue is empty, then there's really no point to keep running. So while queue is not empty, what we're going to do is we're going to get the current size of the queue. Oops. So we get the current size of the queue so we can pop the elements. So you're going to have a for loop for I from 0 to the size. What we're going to do is we're going to pop and get the value of that integer that we have in there. And in Java, there's a function that actually does pop and kind of peek at the same time. It's called poll. So we're going to have int cur, stands for current, equals to q.poll. Right? So that will actually pop the value once it gives you the value. And then what you have is, since we're doing a level traversal, you want to print it out. But the good thing is this is going to be very organized, which means you will see the levels. So you don't actually want to do a print line. You only need a print. You'll print the current node plus a space. All right. And I'll show you why you can get a level out of this once we finish coding this. So then you will want a for to loop through this list, or I shall say the parent child nodes list. So right here, you would do adj list at current. Remember, this is to traverse through current child nodes, that size. So right here, you want to just add them in. Oh, whoops. You want to add at adjacency list at cur dot get j. Now you'll get an error because this gives us an object, not an integer. So you're just gonna have to cast that. Nothing really special there. And that's because I didn't specify type integer here. If I did, then that would be redundant. There you go. So now that that's fixed, I should probably add these two here. All right, so now that that's fixed, the program's basically finished. And to end the level, you just do a printout here. I'll get rid of this one so you can see the level. Before I run the program, I just want to remind you of the tree that we were going to build. It's 0, 2, 1, 3, 4, 5. So now let's go back and hit run. And as you can see, you get a beautiful traversal of our tree. 0, 2, 1, 3, and then the last level was 4 and 5. So now let's talk about what happened here. So, as I demonstrated earlier in the video, this is okay. So this for loop, let's go from inside out. This for loop, as I mentioned earlier, gets the child nodes and then puts them into the queue for later use. Now, what this for loop does is when you add things here, you want to eventually get to them, right? So while this queue isn't empty, it'll take the size and it'll traverse through the nodes that's already in the queue. Now, when you add on to the queue, it doesn't change the size because the size is declared earlier. So when you add on to the queue, that'll happen later. But first, what it does is it traverses through the nodes that is already in that queue. So this is why we get to put this system.out.println here, because this marks a single level, and every time this gets traversed, a new level is created. And within that level, I'm going to repeat myself, this is how you get the child nodes of this level. And that's basically it to a BFS. Sometimes you will be asked to do BFS in a 2D array. Things like, say, so I'm gonna draw some things here. So you have this array. Whoops, I don't know what happened. Looks like they just auto did some stuff. All right, so you have this array, and to say, let's add more columns. Yeah, so you're here in this array, and say you have a fruit. Have this fruit, and you have more fruit here, 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 here. And let's just say this fruit's rotten. And these fruits are all fresh. And what happens is you want to find at one given time, it can only spread to the surrounding cells. So this fruit can only spread here, 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 and here, vice versa. Not vice versa, actually. It can only spread one direction. But basically, it'll infect these, and these. And then these will infect these, and then this one will infect that. And in total, you can see that this was one, all four of these was one single time unit. This one and this one was one time unit, and this one was one time unit. So in total, it took 3 time units to infect all of the oranges. And you can see that in this case, you will use BFS because these surrounding cells are the child nodes of this parent cell. And that's what I mean by implementations of BFS. You have to modify them to adjust to your current situation. So it doesn't always have to be a graph. It could be a 2D array. It could be really anything, but you just have to modify it. The core algorithm is still this. You still use a queue, you still use a while loop, you still get all of its child nodes, and that's just basically the core of BFS. And this is it for this video. I hope you enjoyed it. If you did, feel free to give it a like and subscribe to my channel. If you want to see more coding videos, head over to my playlists or to my channel page. And that'll be it for today. Thank you.